Hello everyone. Today I'll be starting this new topic. This is unit number 5, okay, terpenes. So we finished first 3 units. Fourth unit is alkaloids is left, and fifth unit is terpenes. Terpenes also, that introduction part I told you to watch a video and make that notes, okay. So that part is done. So I'll come directly to the thing. So if you remember terpenes was all about isoprene units, okay, and two isoprene units joined together and get a monoterpenoid, and then sesq and then diterpenoid. So 4 terpene units. So isoprene unit, when it joins, it becomes terpene, okay. So one of the example which we saw there, it was citral, okay. So part of this syllabus is you have to talk about elucidation of structure and synthesis of citral, okay. Now this is called as natural product studies. Now also natural product studies we do, but now it's not of that prime importance as it was previously. The whole organic chemistry is gift of natural products. So people would take some plant, they will extract oil, and they'll try to find out what is that oil, okay. And to find out what is that oil, lot of hard work will go in, and lot of crude chemistry, whatever. Then you put sodium hydroxide, put sulfuric acid, put this, heat it up, and then try to get some structure. And when with all that, finally you will be able to develop a structure, but with that lot of chemistry will develop. So that's what had happened. So we'll see how they discovered the structure of citral, okay. So first we'll know what is citral. Citral is a acyclic terpenoid. We have seen all these examples in the last video. It is widely spread, and basically it is present in lemongrass, okay. How much? 60 to 80%. You must have seen lemongrass. It smells like lemon, okay. It's optically inactive, so no chiral centers. And interesting thing is citral, see, it has two isoprene unit. You remember this? This was the head part. This is the head part, and where it ends is the tail part. Similarly here, if you see, this is the head part and this part is the tail part. So head to tail joint is there. If you remember isoprene, what is isoprene? Isoprene is here double bond and here double bond, and then this goes and attaches, and this comes here, and it is CHO. So it's not terpene, it's terpenoid, because functional group is there, okay. So this is what is citral. Now this CHO, if you see, now I have put CHO top. So there are two possibilities. One CHO can be top, one CHO can be down. So if CHO is top, then if you see, it is getting geometric isomerism, because you look at this carbon. So between CHO and hydrogen, carbon gets first preference, hydrogen gets second preference. And here this part is longer chain. This is carbon, this is carbon. Second bond is all hydrogen. Here second bond is carbon. So this gets first, this gets second. So 1 and 1 is across, 2 and 2 is across. So it is E form, okay. So there are two isomers of citral present. Citral A, which is E form, and the common name is geraniol. So nobody will know citral A, but everybody will know what is geraniol. So geraniol E, GE something, you have to remember like that, okay. So E form is geraniol, and Z form. So if you see here, now this gets first preference, this gets second preference, first preference, second preference, 1 1 together. So this is Z form. It is neral, citral B or neral, Z form, okay. So how they went about the structure elucidation. So in the structure elucidation, the first thing is you have to find out molecular formula. So now for that machine is there, what is called a CHN machine. So it will tell you exactly how many carbons are there, how many hydrogens are there, how many oxygens are there. So that is through instruments they found out. The chemical formula was C10H16O, okay. And now if you know this formula, where is it? Yeah, if you know this formula C10H16O, you can find out degree of unsaturation, okay. So how do we find out degree of unsaturation? Actually, when we do alkaloids, I'll show you exactly how is the formula, but simple thing what you can do is, it is C10. So if it is C10, alkanes, what is the formula? Alkane formula is CN H2N plus 2. So C10, so H should be 2N plus 2. So 2 into 2, that is 20, plus 2, that is 22. But here the hydrogen is 16. So 22 minus 16 is 6. So 6 divided by 2, that is 3. So it's a simple formula. There, if nitrogen is there, if halogens are there, some other formula comes which we'll study later. But basically with this, they got the formula that it is having unsaturation of 3. Now unsaturation can be two things. One is if a molecule is cyclic, that will constitute to unsaturation of 1. Because imagine if you have cyclohexane. So if cyclohexane, what is the formula? C6H12. So C6H12 is alkene, right? And because for alkene, the general formula is CnH2n. So though cyclohexane does not have a double bond, but still it is giving formula of alkene CnH2n. It should have been CnH2n plus 2. So C6H14. But 2 is less. So cyclic constitute of 1 unsaturation. And then if double bond O is there, that is 1. If C double bond C, that is 1. So we don't know what are the 3 unsaturations, but we know 3 unsaturations are there. Now what they did is, they reacted it with bromine. And when they reacted with bromine, what they saw is 2 molecules of bromine was consumed by 1 molecule, and what they got is a tetrabromo structure. Now again, when molecule is there, you can find out by CHN what all things are there. So they found out that 4 bromine got added and nothing got changed. Number of carbon remained same, number of hydrogen remained same, nothing became less. Oxygen also remained 1. 4 bromine got added. So when bromine gets added, if there is double bond, so addition reaction, it undergoes addition reaction, 2 bromine gets added up, right? So, or if triple bond is there, still you can say that 2 bromine can get 2 moles of bromine can get added up and 4 bromines can add. So we are not sure, but we can say mostly 2 double bonds are there, or maybe triple bond is there. And then when they reacted with hydrogen, so they are reducing it. So they saw that 2 moles of H2 was consumed and the number of hydrogen increased by 4. So mostly it looks like 2 double bond, okay? Right. Now they wanted to know what kind of hydrogen is present. What kind of hydrogen is present. So one thing is, hydrogen can be present mostly as 3 forms. One is alcohol, one is ether, one is aldehyde or ketone, so carbonyl. So for carbonyl, if you remember in lab, what do? We react carbonyl with 2,4-DNP, 2,4-dinitrophenylhydrazine. So it forms 2,4-diphenyl-nitrohydrazone and you get yellow precipitate, right? So similarly, instead of 2,4-DNP, you can put something like this, NH2OH. In examination, if you write 2,4-DNP, that also is fine. I'll give full marks. So 2,4-DNP is like this, dinitrophenylhydrazine. It will be like this, okay? 2,4. So NO2 and NO2. So if you use this is 2,4-dinitrophenylhydrazine. If you react with this again H2O will be lost and you get double bond N, and this whole thing remains and you get yellow precipitate. That's what we do in lab. So if now somebody does, they'll be doing this, but it was done previously, so that time I don't think this molecule was there. So they used to use this and they could find out, and they found that it found monooxime. So one thing is very clear, that C double bond O is there, carbonyl group is there. So if carbonyl group is there, it can be either aldehyde or ketone. No other molecule, carboxylic acid, carboxylic acid, alcohols, ethers, none of this reaction will give reaction with hydrazine or this hydroxylamine. So it has to be either ketone or aldehyde. Now one thing is that you cannot confirm ketone. There is no confirmatory test for ketone, but there is confirmatory test for aldehyde. So what happens is, aldehyde, if you know, aldehyde has C double bond OH. Whereas if it was ketone, this is C, here also it is R, here also it is R. So carbon bond is there, carbon bond is there. Now carbon bond you cannot break, carbon bond you cannot break. So you cannot further oxidize it unless you break it up with very drastic conditions. But aldehyde can be easily oxidized to carboxylic acid, C double bond OH CHO. Easily becomes COOH. So that's what we do in lab also. That's what same thing they also did. They reacted it with Tollens reagent, okay, and it gave silver mirror test. So Tollens reagent, what it does is, Tollens reagent is basically silver oxide. It's ammonical silver oxide. So silver oxide, what happens? Silver oxide gets reduced from +1 to 0. Right, it precipitates, and that's what this, when it becomes 0, that means it is metallic silver, and you see a nice silver coating on the test tube. So that is silver. So that is elemental silver, that means its oxidation state is 0. So from +1 it becomes 0. So if this is getting reduced, something has to get oxidized for this reaction to happen, redox reaction. Okay, so this gets reduced and this gets oxidized. So CHO gets oxidized to COOH. So since it gave positive test for tolerance reagent, one thing was for sure, that this reagent has aldehyde group. Okay, and that's why it is able to oxidize this aldehyde group into COOH. So they initially found out that formula was C10H16O. So out of that, one is CHO, so they put out CHO. What is left is C9H15, and when they reacted with it, they got some compound. They don't know exactly what it is, but they kept the name xeranic acid because CHO got oxidized to COOH. So one thing is sure, this Citral has CHO group. Now also what did UV had developed by that time, and they saw that it shows maximum absorption. UV spectroscopy had shown a maximum absorption at 235 nanometer. So generally if it is just carbonyl, no, if it is just aldehyde or ketone, it will show around 180 nanometer. But if it is showing 235, no, it means alpha beta unsaturated ketone or aldehyde is there. So we know aldehyde, it is there. So it must be something like a double bond is here and CHO is there. So alpha beta unsaturated aldehyde is there, which was confirmed by this UV studies. Okay, now they want to know what is the this nature of the citral as terpenoid. So one thing is very clear, it has 3 degrees of unsaturation that we found out because of the formula, right? And then we saw one aldehyde is there, right? And then what we saw, it was reacting with 2 moles of bromine. It was getting reduced by 2 moles of hydrogen. So 2 double bonds also there. So 2 double bonds plus 1 CHO. So that constitutes to total 3 degrees of unsaturation. So it cannot be cyclic. So one thing is very clear, it is a acyclic terpenoid. Okay, so these are important things. Till now the study, see, all this would have taken a long time, almost 6 months to find out till this much, that it has aldehyde and acyclic terpenoid. Generally when you do a natural product study, 1 molecule, your PhD you'll get. But now it's faster because we do a lot of NMR studies. We don't have to do all of these things. And then what they did is they reacted it with potassium hydrogen sulfate. Now potassium hydrogen sulfate is a dehydrating agent, it absorbs water. And then when they heated it, they got this molecule, paracymene. Now this paracymene, what happens is, they had some idea that must be the citral, and they formed this. And this paracymene was known till then previously. Okay, they had characterized completely, and they saw that all the physical properties, melting point, boiling point, everything, and the chemical properties, everything matched exactly like that of paracymene. So they knew when you react with KHSO4, when you dehydrate it, it forms paracymene. So it gives us certain idea that this must be the kind of structure citral is having. This will be the carbon skeleton, because this is the paracymene. So they felt this must be the structure, and we don't know where is double bond, where is CHO. Okay, and then what they did is they oxidized. Right, now what they did is they oxidized citral with KMnO4 OH minus, and then in basic medium KMnO4, and then they oxidized with chromic acid Cr2O3, but basically we put acid, so it become H2CrO4. Okay, so they reacted citral in 2 steps, first with KMnO4 OH minus and Cr2O3. So if you know what it does, KMnO4 OH minus, it makes it breaks up double bond. Okay, like ozonolysis it does, exactly like ozonolysis, it breaks up and forms 2 side C double bond O, C double bond O. And if you put acid, chromic acid, it will oxidize the aldehyde to carboxylic acid. So that's what they wanted to see, and what they did is, when they did this, they could isolate these 3 structures. These 3 structures are known. So when they did for citral, they got levulinic acid, they got acetone, and they got oxalic acid. So you have to write all this in examination. Okay, it's a simple 10 marks or 20 marks question. Elucidate structure of citral. So what they got is levulinic acid. So if you know the IUPAC name, it will be much better. So it is 1, 2, 3, 4, 5. Acid gets more preference than ketone. So you start from here, 1, 2, 3, 4, 5. So it is pentanoic acid. So it is 4-oxopentanoic acid. They got 4-oxopentanoic acid, acetone plus oxalic acid. And then they also did ozone-lysis. Ozone-lysis followed by hydrolysis in presence of zinc. So again they got is acetone, glyoxal and 4-oxopentanal. That time they had got pentanoic acid, 4-oxopentanoic acid, and here they got 4-oxopentanal. So when they mixed up these two structures, these two analyses, and they came up with this structure of citral, right? How? So, a lot of retro and a lot of brain would have got. We'll go first step and direct step and we'll know. If this is the structure, what ozone-lysis followed by CHO, followed by zinc water will give. So many times we have done this, okay? So if you do ozone-lysis, this double bond breaks up and you should get C double bond O. And here since hydrogen is there, so what you'll get is C double bond O, here aldehyde. So what you should get is CHO. That's what you are getting, CHO. Here what should happen? You get a C double bond O ketone, and here also it becomes breaks. It should become C double bond OH. So you got this one C double bond O. Then you came here and you got C double bond OH, C double bond OH, and you get acetone. Okay, and you get acetone. So all these three structures matched. So they know it is this molecule, the citral is this molecule for sure. Apart from that, we saw with ChemNO4 what happens. Exactly like ozone-lysis happened. Only thing is, if any aldehyde is there, it will oxidize it to acid. So here also pretty much same thing. It will break up initially and this will form C double bond O. This will also form C double bond O. But here it will form C double bond O and H. Right? So that is aldehyde. This is aldehyde. So aldehyde will get oxidized to COH. So you should get C double bond OOH. Here also you get C double bond OOH. And here you will get ketone. Now just now I told that ketone cannot be further oxidized because carbon-carbon bond cannot break. So ketone will remain ketone, but this will become COH. So did we get COH? Yes, we got COH. And here what we'll get is C double bond O, and here it is CHO, but it will get oxidized to COH. So what I should get is this C double bond O, this C double bond O, further here, and you get COH. And this one breaks to acetone. Acetone cannot be further oxidized because it is ketone. And these are the three structures. So with all these structures together, they concluded that the molecule is citral. Okay, they concluded molecule is citral. Now, still it has a lot of speculation. To confirm, no, one of the best way now also, when you do structure synthesis, when you find out any new molecule, even when you do synthesis in lab, normal synthetic reactions you do, you are not very sure what product is formed because NMR is basically some lines. So it gives you great indication. You are 99% sure, but for that 1%, no, best way is if you are able to crystallize that molecule, because crystallization is like photography, and that molecule may be liquid. So you can always make some derivative of it. So if OH is there, make it paranato benzoate kind of things. So you make it polar so that it crystallizes. Other thing what they used to do is try to synthesize it, and if you synthesize and you see that you are getting same molecule, then same physical, same chemical properties, then you know that it is the same molecule. So that's what it was confirmed by synthesis, but it's not great method. Synthesis also can fail you a lot, but synthesis you have to do to make your point more strong. So they took acetylene or ethine and they reacted with sodium liquid ammonia. This is Birch reagent, correct? And so what they get is C minus Na plus, and they reacted with, I don't know why they use this, because this should generally if you use this it will reduce double bond. They should have used NaH. Okay, let us not use this because see only for acetylene it will be this reaction might be working. Let us know proper organic chemistry. Okay, so put some good base. I put something like LDA is a way, or you can use NaNH2. That is a wonderful base. Okay, soda amide. Na plus NH2 minus. So if they use, they used that, worked for them, but let us learn good organic chemistry. So you never use this reaction. You use sodamide NaNH2. So, and now you know this proton is acidic because this is sp hybridized. Since it is sp hybridized, it has more S character, so it is more electronegative. So this proton is acidic. It removes this proton, becomes ammonia, and you got HC triple bond C minus Na plus. Okay. Then they reacted with acetone. So what will happen if it reacts with acetone? This will come here. Wow, it will come here. It will attack here. This will come up, and you put hydrolysis, becomes OH, and this goes and adds HC triple bond C OH CH3 CH3. And they used H2PD BSO4. So not just putting H2PDC. If you are using BSO4, BSO4 is poisoning reagent. So if you use BSO4 or quinoline, either of them, it is called as Lindlar's catalyst. So Lindlar's catalyst is called as poisoning reagent, and they reduces the alkyne to alkene, and the addition of hydrogen is always cis addition. Okay, when you do Birch reduction, you always get trans alkene, but when you do hydrogenation using Lindlar's catalyst, you always get cis alkene. So you got here there is no question of cis and trans because both are hydrogen, but you should know this. Okay, it got reduced to alkene, and then they used this PBr3 and they got CH2Br. Now this reaction is a bit unknown, so we'll leave it at that. Just remember this. And then they reacted with this. What is this? Ethyl malanoate, right? No, sorry, it is ethyl acetoacetate. We did this last semester. So if you are having CH3 C double bond O, CH2 C double bond O, OET. So this is called as active methylene group. This hydrogen is, these two hydrogen, this hydrogen is acidic. So if you use base, you cannot remove both the protons because small carbon cannot hold two negative charges at one time, but you can do step by step. So when you use this negative charge, this proton is lost. Why? Because conjugate base is stable. If it is acidic, that means conjugate base should be weak, weak base, because it is strong acid, not strong acid, but it is acidic. So if this proton is acid, that means conjugate base should be stable. So once you remove this proton, you get negative charge here, and this negative charge is stabilized here. Also negative charge is stabilized here through conjugation. That's what they did. They used this base, and this minus goes, and it will go and attack here. This minus charge will go and attack here, and this Br will leave, and you get exactly same thing. If I show you from here, so this bond is there, double bond, then CH2, Br has gone, and this part has joined. So this carbon has joined, and this carbon next to it is COOET, and this part is C double bond O CH3, right? And then you use OH minus. So OH minus and water use, basically you see this. What is this? This is ester, no? R C double bond O, C double bond O, O R minus. So if you hydrolyze ester in acid or base, what do you get? Esters break up, you get acid plus alcohol. So that's what you are getting, C double bond O, OH, and here you are having C double bond O. Now we studied last semester that if acid COOH is beta to C double bond O, okay, then we saw that mechanism also, how this happens. This goes and attacks and CO2 is lost. Basically, if beta ketonic group is there, beta C double bond O, ketonic or aldehydic or COH, anything is there, but if beside a COH, beside means beta position, not alpha, beta position of CO is there, then if you heat it, CO2 is lost. Very, very important, okay, don't forget. So that's what they did, and what they got is this molecule CO2 is lost, and you get this molecule, and then they again reacted it with this molecule. This is a Grignard reagent, CMgBr triple bond COET. Now this negative charge will go. Where negative charge will go and attack? It will attack, of course, this carbonyl group. This comes up here, and you get OH, and this you get this molecule, and then you react with H2PDBSO4. Now again very important, okay, you are using Lindlar's catalyst. BSO4 is poisonous reagent. It will not touch alkene, it will touch only and only alkyne, and that to addition of hydrogen will be cis addition. So one from same side both hydrogen will get added, okay, and that's what is happening. Anyway, so you get this molecule, and when you hydrolyze it, you're getting this Citral B. Okay, so this was the Niral, how they synthesized. We no need to know both of them, but it will be simple actually. Here, if they would have done Birch reduction, you would have got the geraniol. But if they are using Lindlar's catalyst, what you're getting is Niral. Okay, thank you.